So now we're going to determine the equivalence classes of our relation from the last video. So we want to determine the equivalence classes for the relation R defined on Z by x relates to y if 11x minus 5y is even. So in our last video, we showed that this was an equivalence relation. We showed that it was reflexive, symmetric, and transitive. And now what I want us to do is find the equivalence classes. So the first thing you're going to do is take an element out of Z and find its equivalence class. So let's start with 0. Let's find the equivalence class of 0. So remember that this is all the elements x and z, where x is related to 0. So this is all the elements x and z, where 11x minus 5 times 0 is even. But you can really just leave out the 5 times 0. That's just 0. So it's 11x is even. Well, the only way for 11x to be even, because 11 is odd, is for x to be even. So this is the same thing as x and z, where x is even. So what would this set consist of? This equivalence class, it would have 0, 2 or negative 2, so plus or minus 2, plus or minus 4, plus or minus 6, and so on. So there's one of my equivalence classes right there, the equivalence class of 0. Now, I'm going to say that we know that there is at least one other equivalence class. And why do we know this? If you look at this equivalence class does not contain every integer. It only contains the even ones. And so in particular, what we need to do to find a different equivalence class, a distinct one, what you should do is you should look for an element of Z that is not in this equivalence class. So in particular, I noticed that 1 is not in the equivalence class of 0. So I'm going to find the equivalence class of 1 now. So this is all the elements in Z that are related to 1. So using our relation, it's all the elements in Z where 11x minus 5 is even. Well, in order for that to be even, 11x has to be odd. X has to be odd. So this is x and z, where x is odd. Because this 5 is odd, if I want the overall result to be even, I need 11x to be odd. So in particular, x needs to be odd. So I can write out elements in this equivalence class now. Equivalence class of 1 contains plus or minus 1, plus or minus 3, plus or minus 5. And now if I look at my two equivalence classes, my equivalence class of 0 and my equivalence class of 1, every integer is in one of those two sets. So I have found the equivalence classes for this relation. I can now say that R has two distinct equivalence classes, and those equivalence classes are the equivalence class of 0 and the equivalence class of 1. And those are my distinct equivalence classes.